Now we are going to discuss the concepts of stacks and queues. This is a quite short chapter. These two data structures are implemented in the Java Collections framework. We will first discuss the generic concepts of stacks and then the concept of queues, and later also discuss how we can use them through the Java Collections framework. We first start with the concept of stacks. A stack is very similar to a linked list. The difference is, remember, in the case of a linked list, you could be inserting a new element to the start or to the beginning or the end or anywhere in the middle of the list. In the case of a stack, you always append your element to the end of the list. It's not possible to insert to the beginning or to a specific index. You can only put a new element at the bottom, at the end, sorry. When you're trying to remove an element, then you remove the element this time again from the end. Therefore, the last element which was added into the stack becomes the first one to get out. That's where the name last in first out or LIFO comes from. We have two basic operations, two basic methods for this. These are called the push and pop structures. So we can consider a stack as something like this. So this will be our stack, because it's actually just like a stack or pile of elements put one on top of the other. So at the moment we have an empty stack. So if you try to pop anything out of this stack, you will get an error because there's nothing in the stack. Now, when you want to put a new element into the stack, you do it by calling the push method. And we say you're pushing something onto the stack. So the element you push goes to the top of the stack, but at the moment we have an empty stack. So the first item you put will go to, will be the only element in the stack. So let's say we're just pushing in an item named A, so it goes to the bottom. Okay. Now you can consider this stack as a pile of plates on top of each other. So it was like initially I had no plates on my table. Now I have placed plate A on the table. Now if I have a new plate, say plate B, all I can do is I can put plate B on top of A. It is not possible to put B under A. You can do it only by first removing A, putting B, then putting A. Okay? If A is already there on the table, and if you try to put B, B would go on top of A. So let's say later you push another plate, another item, say C. Now, if you want to take a plate, the plate you will get will be the one on the top. Here in our example, it will be plate C. You cannot take plate B directly. Okay? So when you're trying to get an item, retrieve an item from the stack, you will retrieve it from the top of the stack again. Therefore, what you're going to be removing will be item C. So it will be like this is removed. So now the new top of the stack is B. Okay. Now, if you want to insert a new element, again, that would go on top of D. If you remove one, the first one to be removed, sorry, would be D. Then if you remove once again, then you would be removing B. So this is how it works. And to manage this, what I need to do is actually, I need to keep something that keeps track of the top of the stack. Okay, so we will have a top pointer. So for an initially created stack, everything, remember, in the stack is there's nothing in the stack. We start with an empty stack. So our top pointer will be pointing here, which means there's nothing in the stack. When we want to insert A, what happens will be an entry will be created, it will be placed in the stack, and the top will be pointing here. So the top always points to where the new element will be inserted, or the next element to be popped will be popped from. So you either insert B here and move top, or if you want to remove an element, again the top points to where we're going to remove the element from. So we are going to remove it from here, so this will be removed. So this is in general how a stack actually works. So for the abstract data type definition of the stack, we talk about a stack. We're going to denote it by S. The item to be pushed onto the stack or popped from the stack will be denoted by E, standing for element or item. And B will be a Boolean value. So the methods will be defined as initializing the stack, some stack S. You should be also able to destroy a stack. So that would be destroy stack S. You should be able to check if the stack is empty or not. So stack empty would return true if the stack is empty, false otherwise. And stack full would return true if the stack is full, otherwise it will return false. Note that conceptually, we could implement a stack of infinite size. In that case, we would not need the stack full method, because since the size of the stack is infinite, it will never be full. But in reality, typically there will be a limit on the stack, and we need to check before inserting a new item into the stack by before pushing in a new item onto the stack, we should be checking if the stack is full or not. Otherwise, we will have the famous stack overflow problem. And definitely we will need these push and pop methods. Push needs S for showing which stack it is, and E will be the element to be pushed onto the stack, and pop will be removing that element, the top element. So let's look at an example. Assume that we want to write a procedure or method, whatever, to replace the elements of a non-empty stack, assuming all the elements are integers, and we want to find their sum. So in other words, you're given a stack with at least one integer in it. There could be more integers. And the question you're asked is, how do you find the sum of all elements in the stack? So our precondition is that we're given a non-empty stack of integers. And the post condition is when our method ends, in the stack there will be one and only one element, and that element will contain the sum of all elements that were previously stored on that stack. So the algorithm would be as follows. Note that this is not a Java code. This is just a generic algorithm. It could be implemented in any programming language as long as you have the data structure for a stack and push and pop operations. So whatever the element is, in our case that was an integer, we define a variable, say E1. So remember, our precondition was that the stack is non-empty. So I'm sure that there's at least one element in the stack. So whatever we have in the stack, pop one from the stack and put it in variable E1. Note that in the stack we could have more than one element, so it would be the one at the top. That's what we have in E1 at the moment. So now when we do this, first of all, when we execute this pop instruction, the size of the stack will decrease by 1 because we have removed one element. So the stack now might have become empty. Earlier we were sure that at least there was one element, but since we already removed one, now it may have become empty, or maybe there are more elements. So while the stack is not empty, keep on doing these 3 indented statements. Since if I'm here, I'm sure that the stack is not empty, again take the new top element and put it in E2. Note that these are 2 separate integers, one in E1 and one in E2. So I know I have the, if you look at the initial stack, the top element has been copied to E1 and the element below the top has been copied to E2, and now the stack is smaller by 2 elements. So I find the sum E1 plus E2 and push this sum into the stack. So what happened? I removed 2 elements from the stack, pushed in the sum, so I pushed in one element. So if you look at the net result, at the end of this push method call, the size of the stack has decreased by 1, and the top element contains the sum of the previous 2 top elements. So I'm fine because it contains E1 plus E2, but now I want to repeat this loop over and over. Remember that while I was entering the loop, E1 had the value, it had the top value. So again, remove that top value, put it in E1 so that when you iterate, you can still talk about E1, which was the sum of the previous 2 top values, and you get the third element from the top in E2 and add it on the sum. So if you do this in a repeated manner, you will always be keeping the sum of all elements up to that point in the stack, and when you reach the end of the loop, which is when the stack is really empty, in the variable E1, remember in the last iteration, you get the sum into variable E1, and you come here to the condition and see the stack is empty, so you exit the loop. So in E1, we have the sum of all elements up to that point. So remember our post condition. Our post condition said return the result in the stack. The stack should contain single element, which is the sum of all of them. So you push that E1 back into the stack. Okay. Now, as you have realized, we're just a little bit in a redundant manner pushing in and out the same variable, the same value several times, but this is a very generic solution that will help us in many cases. Let's look at another example. Remember that actually the concept of a stack is very important in computer science. It's used in almost all fields of science, but one of the most important uses of stacks is in the design of compilers, in the design of programming languages. For example, we have mathematical expressions, which is composed of parentheses, or we have pieces of code segments, where we have open close parentheses or braces. And we want them always to be matching. In other words, you should never close a parentheses or brace before it has been opened, and you should never end up in an expression or in a code segment with a case where you have not closed all of the parentheses. So this is called checking for balanced braces or balanced parentheses, whether depending on whether you're looking at braces or parentheses. So we want them to be always balanced. Now, the first solution that comes to mind would be you count the number of open braces and you also count the number of closed braces. If they are equal, you could say, well, they're balanced because their numbers are equal, but Unfortunately, that's not always true. For example, you could have an expression like this: open brace, A, B, close brace, C, open brace. Now, if you try to count the number of open and close braces, you have 1, 2 open braces and 2 close braces. So they're equal. But you cannot claim these are balanced braces, because here we have closed a brace which has not been opened, and here we're opening that brace, but it's too late. So counting the number of open and closed braces and removing them is not sufficient to solve this problem. So we need a better solution. One thing you can do is, when you encounter a closed brace, you find it's matching open brace. There should be a matching open brace. And when you come to the end of the input, you should have all of the braces that have been opened. So you can simply insert an open brace whenever you see one, and whenever you see a closed brace, you can try to pop it out of the stack. So when you see an open brace, push onto the stack. When you see a closed brace, pop out of the stack. And you should never fall into the scenario where you try to pop something, a brace from the stack, but there is none. If that happens, it shows that there was an imbalance, even if the total number of open and closed braces are equivalent. So this algorithm will actually do that. We first create an empty stack. We're going to read from the input. Currently, by the way, again, this is a pseudocode. This is not full Java code. We keep a variable named balance so far. I'm just reading the input, and so far it's balanced because I have not seen anything yet. So by default, it's true. And we have a counter which is initially set to 0. So while the input is balanced so far, which is initially true, and I is less than the length of the input string, we're reading, say, from a string. So that means we have not reached the end of the input. So while it's balanced and we have not reached the end, keep on doing it. So keep on executing this loop body. So what are we doing in the loop body? Well, take the next character and increment the character count by 1. If that character you have read is an open brace, push it onto the stack. If it's a closed brace, check if the stack is empty. If the stack is not empty, then remove that open brace from the stack. Otherwise, if you've seen a closed brace, but the stack is empty, there is a problem. So you set the balance so far variable to false, which will cause you to terminate the loop, the while loop, immediately, not trying to finish till the end. So the moment it becomes unbalanced, you cannot fix it. There's a problem with this expression. It has to be corrected. So when you get out of this loop, either balance so far is true, so you've reached the end of the loop. You have not seen any unbalanced cases during looking at the input, but this is not sufficient. You should also make sure that there has not been left any open brace which has not been closed yet. So it is possible that you never fell into this problem, You never fell into the case where you've seen a closed brace, but the stack was empty. That didn't happen. So balance so far was true. But there is some open brace which has not been closed. In that case, again, it's not a balanced input. So it should give an error. Or if balance so far was false, I don't care about the stack at all. Again, it's false. So again, we go to the else and say it's not balanced. But if it's balanced so far and there's no open brace left in the stack, that means I've closed all open braces. So my input would have balanced braces. So another nice usage of the stack is the famous problem of towers of Hanoi. It was defined in 1883 by Edward Lucas, a French mathematician. It is a very generic problem actually. In general, people take 3 poles and n disks, and in general they accept 7 for n, but the problem is more generic. So you can have 3 poles and more disks. Actually, it's also possible to implement it with more poles. That's a more generic version of the problem. Anyways, initially there are several stacks. The stacks are of different sizes. Each stack is of a different size, and all of these disks are stacked on the first pole, such that the largest pole is at the bottom, and the largest disk is at the bottom, and all disks are ordered in a way that you never have a large disk on top of a small disk. And what we want to do is we want to move all of these disks from one pole to the other, but never we should put a large disk on a small disk. And also we can move the disks one by one, and there's nowhere else we can put the disks. There are only 3 holes, so you should put these disks on these 3 holes. So let's look at a nice demo at towersofhanoi.info. Sorry. Okay, here we go. So as I said, the problem could be more generic. So here you can increase the number of pegs. A peg is these poles, peg or pole, the same thing. And we have the disks. As you can see, there are a variable number of disks, but it's always the larger is at the bottom. So you can change the number of disks here, the number of pegs or the poles here. You can change the speed here. You can have a 3D representation or a 2D. That's a nice one. So let's just analyze how things are working. Unfortunately, it's not possible to pause the simulation here. So we're just I'm just going to explain it fast. So the idea is all of these disks are placed on top of this on this pole, and we want to carry all of these disks from this pole to one of the other 2. And while doing this operation, I have to take the disks one by one, and I should never put a large disk on top of a small disk. So let's see how the solution is. Now, as I said, I will not be able to pause it. You can pause the video if you wish. And note that the solution is actually a quite recursive solution. Okay, so let's examine it. We put the first one in the second. Now we have to put the larger one here, so the smaller one comes on top of it. Now this is larger than the other 2. We put this. See, this is the way you can put the second one here and the first one comes on top of that. And now it repeats, as you can see. This one goes left, this one goes here, and now this one we can place here. Take this one here, so that you can put this one on top of this one. Now we can carry this one here. See, again, recursion starts. We move this one here, take this one out, take this one here, take this one on top of this, so that you can put this one here. Now, we would like to get rid of them. This one here, this one here, so that now this is available. This one can move to the second pole. Take this one here. This goes down here. This one comes here, so that I can put this one on the second pole. Now take the smallest one to the first one. This one goes to the second. And we're finally done. In a total of 31 moves, it's complete. Now, how would you implement this? This is a question. And you should have a generic solution that can take n disks. Instead of 5 disks, for example, we could have said 7 disks. How do you implement it? Now let's devise a solution to this problem. The solution is actually much simpler than you would imagine. Now remember, we have 3 poles, say 1, 2, and 3. And we have the disks, say, on pole 1 like this. So what I'm going to do is name this as source and say this one as a destination, and name the other one as auxiliary. Let me write it better. Okay. So the idea is actually to take these top elements from here and move them temporarily to the auxiliary, so they will not be here anymore, so that now I can take this large one in 1 and put it in, oops, sorry, my mistake, put it in the destination pole, so it will not be here anymore. Okay. Now, if I do this, actually, I have done most of the work that needs to be done. Then, from the auxiliary, now I should try to move these 3 elements here into destination. So now, if you look at this final step is just like the original problem. Just the size is decreased by 1. I was earlier trying to move n elements from one pole to the other. Now I'm trying to move n minus 1 disks from one pole to the other. Except that now the names should change. This is not source anymore, auxiliary anymore. Now this is source. So, for example, you might be making this one auxiliary or whatever. So we're just renaming those names as source and auxiliary. So the algorithm is, as in these bullets here, it's actually a 3-step solution, as in here. You move a tower of n minus 1, leaving the last one, disk n, in source, and taking all of those above the largest disk from source to auxiliary, and moving that largest disk to destination, which is what you wanted. Then remember those n-1 that were moved to auxiliary. Now try to move them from auxiliary to destination. Okay. For the implementation, let's open this project. So if you look at the solution, everything is actually implemented here. This is the whole solution. Here we have the move method, which we are going to use here. And in the main methods here, we just have an example scenario created, like we have put 4 disks in this case in pole A, which would be our, for example, source. So we create 3 poles, A, B, and C, and we put all of them in one pole. 4 is the largest one, so you first push 4, that goes to the bottom. 3 goes on top of 4, 2 goes on top of 3, and 1 is at the top. Okay, so once this is done, you just print the initial state, call the solve method, and then print the final state. So what does the solve method do? Solve method takes n, which is the number of disks. See, we have called it with 4 because I've inserted 4 elements. Then the 3, let me maximize it. The 3 poles, source, auxiliary, and destination. And all it does is it takes, rather than n, it takes n elements and sends n-1 of them from source to auxiliary, moves 1 element, the remaining one, which is the largest one, to destination, and then moves n-1 elements, this time from auxiliary to destination, just as we discussed here in the algorithm. But note that in the initial case, I was sending A, B, C in this order to source, auxiliary, destination. So source was A, destination was C. But when you're calling the solve method in a recursive manner, see, the name of the method itself is solve. When you're calling the solve method in a recursive manner, you're changing the order from source, auxiliary, destination to source, destination, auxiliary. And in the second recursive call for solve, this time you're changing it as auxiliary, source, destination. And this is all you do. Till when? Until n is greater than 0. Because if n is 0, trying to shift or move n-1 disks would not make any sense. And how about the move method, which is called here? It's just taking 1 from the pole and pushing it onto the 2 pole. See, we're calling from pop to push. That's it. And we have 2 print lines here just to show what's going on. That's it. So move is quite simple. Actually, the whole algorithm is quite simple. But this could be implemented this way because we now have a new data structure called stack. Note that we're implementing the poles as stacks. Here we have stack of integer. Just like the list, you could have stack of string, stack of anything you want. And also don't forget that you cannot create stack of int. You have to use the wrapper class integer for that. So it's quite easily done actually. How about the complexity of the Towers of Hanoi algorithm? Assuming that we have n disks, let Tn be the minimum number of moves required to solve this problem. So remember the algorithm, we're actually moving towers of n-1 disks twice, and between these 2 moves, we're moving the largest disk once. Therefore, Tn would be 2 times Tn minus 1 because we're moving the towers of height n minus 1 twice, plus 1 for moving the large disk. Now, if we look at this equation and rewrite it for Tn minus 1 and Tn minus 2, we get equations 2 and 3. Now, substituting Tn minus 2 in equation 2, we get equation 4. And then substituting Tn minus 1 in equation 1, we get equation 5. So a general solution for this problem would be given in equation 6, which is 2 to the n times T0, where T0 is 1, plus 2 to the n minus 1 plus 2 to the n minus 2, all the way down to 1. This geometric progression series has the sum of 2 to the n plus 1 minus 1. Therefore, the Tn, which was the number of moves that was required to solve the problem, would have complexity of big O of 2 to the n plus 1 minus 1. We know we can discard this minus 1 here, and for this 2 to the n plus 1, actually it is equivalent to big O of 2 to the n.